All right, so in this video, we're going to look at volumes of solids of revolution. We have two methods for performing solids or calculating the volumes of the solid of revolution. There is the disk and washer method. These are basically the same method. Textbooks often talk about them a little bit separately, but really they're the same thing. The only real difference is that in the disk method, there is no inner radius. It's equal to 0. But you can just remember the washer formula. And then if you have no inner radius, you set it equal to 0. And that's usually the way I like to think about it. The idea of the washer method is based on the idea that you calculate the area at the base of your cylinder, which is typically a circle or a circle with a hole in the middle, an annulus. And once you calculate that area, which is pi r squared, then you integrate it over the height of the cylinder. Now in the shell method is given here. And the idea here is that it's you're taking the cylinder as a hollow cylinder, and then you are integrating it as you change the radii. So you're adding up along different size radii. You're calculating essentially the surface area of the cylinder and then multiplying it by a small width. So we have 2 pi RH. So the circumference around the surface area of the cylinder is our 2 pi r, and then the height is given by typically the functions. Now, which method you use typically depends on which radii, which axis of rotation you're using. So the general rule of thumb that I like, the way I like to think of this is that if you're using the washer method and your functions are functions of x, and then you use the washer method if you're rotating around the x-axis or a line parallel to the x-axis, so that the function variable and the axis of rotation are the same. In the shell method, they're opposite of each other. So if you have functions of x, but you're rotating around the y-axis or a line parallel to the y-axis, then you use the shell method. And then the reverse is also true. So if you have a function of y, you use the washer method if you're rotating around the y-axis or a line parallel to the y-axis. And in the if you have a function of y and you're rotating around the x-axis, again, yx, then you're using the shell method. Now you can technically use either method almost all the time, as long as you can do the algebra that you need to do in order to put the variables in the right form. We're going to look at several different worked examples in this next couple of videos where we are doing them both ways. And so in order to do that, I'm rotated around different axes. In order to do that, I picked a function for our example that is relatively easy to solve, to switch variables. Sometimes you don't really have much of a choice. You might get a function which is like cubic in y, in which case it may be impossible to solve for y in terms of x alone, in which case you're stuck integrating in the y variables. Or it may be doable, but it may require nasty things like completing the square and stuff like that, would take a lot of time. I picked an example that isn't going to be that much of a mess, but nonetheless, and everything will be nice and easy to integrate. But nonetheless, in principle, you can do these all the time with either method, as long as you use the right combination of method and variable and axis of rotation. But usually what you want to do is you want to pick the one that is the easiest to do given the way the information is presented to you, so that you don't have to do all that intermediate algebra, and so that you don't get a really nasty, messy function because you're trying to solve for things that you really weren't meant to solve for. However, in these videos, these next couple worked examples, I'm going to use my region and I'm going to rotate it around both the x and the y-axis, and then two lines which are not the x or the y-axis. And then we'll do them in both the shell and the washer method in each case. Partly so that you can see that, yeah, they should give you the same answer, because again, it shouldn't matter. The main difference will be the algebra and how many fractions you end up dealing with and things like that. And again, how much extra work do you want to do? In principle, you can do them either way all the time. And I find personally that when I practice these, I got really good at the methods and when to use which one when I did lots of problems both ways. It's a good way to check your answer, make sure your answer is right, and just to get comfortable with the differences, what to do when. On an exam, obviously, you don't really have time to do that, but that's a good way to get comfortable on the homework. All right, so the worked example that I'm going to use is going to be based on this region. It's basically a triangular region. It's bounded on this side by the line y equals 3x plus 1, on the bottom by y equals 1, and on the right side by x equals 2. And we have an intersection down here at 0, 1 for this corner, and an intersection up here at 2, 7 for the second corner. All right, so our first example we're going to do is we're going to rotate this region around the x-axis. So it's a good idea on your drawing to always remind yourself which axis you're rotating around. It's a good visual reminder to get yourself oriented. There's a lot of moving parts in these problems, and particularly when you're first learning how to do them, keeping all of those moving parts straight can be complicated. Now, the best method, given that our function is given to us in terms of x, 3x plus 1, and we're rotating around the x-axis, the best and easiest method to do this with is the washer method. And so that's the one that we're going to tackle first. Now, the washer method has our inner and outer radii. So the drawings here in black. The inner radii is the difference between the axis of rotation and the bottom of our region. Now, it doesn't have to be off the axis of rotation everywhere. It just has to be off the axis of rotation somewhere. So this could be a function that touches at one point, but is away from the axis at other points. But here, it's just a constant line. Our inner radius is 1, and that goes into our formula squared. And then the outer radius is the distance from the axis of rotation to the function, this straight line, y equals 3x plus 1. So that outer radius goes into our function squared. The limits are x equals 0 here and x equals 2 here. And we do have to do a little bit of algebra for this. If we FOIL this out, remember, it's not, you can't distribute powers. You have to FOIL. So 3x times 3x is 9x squared. 3x times 1 plus 3x times 1 is 6x. 1 squared is 1. Then minus our inner radius. And this reduces to 9x squared plus 6x. And when we integrate that, we get 3x cubed and 3x squared, and we plug in our 0 and 2, and we end up with 24 and 12, which is 36 pi. So that's the volume of our rotated region. Now, to do the shell method, we have to first solve our function for x in terms of y. So we have to do a little bit of algebra, and this is why, part of the reason why you don't want to do the shell method in this case, because you have to do this extra work. And in this example, one of the things that we end up with is we end up with this fraction that we have to then carry through the whole problem. And I mean, I can do fractions, but it is harder and slower to do it with fractions than without. So, all right, so now the shell method, let's go back to our graph. The shell method, remember, is based on the height and the radius. So the height of each cylinder as we rotate it around the x-axis, the height is given by, because of the orientation that we have, the height is the top function minus the bottom function. It's the difference of our two functions. But because we're oriented sideways and not upright like we normally are, it's the rightmost function minus the leftmost function. And the rightmost function is x equals 2, farthest away from the y-axis. That's our most positive. And then the bottom function, the leftmost function, is our line, which we just solved for, 1/3 y minus 1. So this portion right here, inside the square brackets, this is the height of our function, the rightmost function minus the leftmost function. And then the radius of each of our cylinders is basically how far that height that we're measuring is from the axis of rotation, which is just y in this case. It's the height. And so that's our radius. Radius times height, integrate, and again, the y values are derived from the y. So this was x equals 0 before, but this is y equals 1. And up to here, this was x equals 2, but this is actually y equals 7. And so, okay, so we get this crazy function. We have to do a little bit of algebra. We simplify by distributing the y. And then we have a 1/3 y term and a 2y term, which we combine into 7/3 y. And then we can safely integrate that. Y cubed, y squared becomes y cubed with another 3 in the denominator. Y becomes y squared with another 2 in the denominator. And then we have to plug in 1 and 7. You can see all these fractions that we didn't have before that are new. 7 cubed is 343. This is 7 squared, but then times another 7 is also 343. And then we have to subtract a negative, so this becomes a positive, plugging in 1, and then subtract the positive gives us a negative, plugging in 1. And when you throw all of this into your calculator, you get 18. And 18 times 2 pi is 36 pi. And this is the important thing. Again, both of these methods work. They give us exactly the same answer, which is what you expect that they should do if you're doing, if the methods are set up correctly. It's the same volume, but we're just thinking about it, breaking it down into different ways, and we got the same answer. But it's really clear from this example why the washer method is better for this particular situation. A function of x, you don't have to do any pre-algebra. The worst thing you have to do is FOIL this binomial. And then from there on, it's just nice whole numbers. You have a 0 as a boundary in this particular case, which makes things much nicer. And you get the answer. Whereas in the shell method, not only did you have to first solve for the height, the bottom leftmost height function in terms of y instead of x, but then you had the difference in heights that you had to then simplify. You ended up with all these fractions, which you then had to multiply through and add and do all these, if you're doing these by hand, common denominators, pain in the ass. And what you end up with is the same answer. You did a lot more work, but you got the same answer. So again, if you're just trying to get the answer, the easiest way to victory in this example, in this particular problem, is the washer method. Now, in the next couple of videos, we're going to do rotating around the y-axis and a couple other axes with this same region. And again, both the washer and the shell method. So again, depending on what axis of rotation you're looking at, you want to watch maybe all of them.